We'll continue the lesson about linear regression. We only talk about regression with just one variable last time, and the data was made by me. It was the ideal data made by me. And today we are going over a real case with multiple variables, so what we call multiple regression. So last time we did it just with one single variable, right? So this time we do multiple regression, which means the relationship between two or more independent variable and one target variable. And we'll also mention polynomial regression, which means you are not just doing x, you are doing n degree on the nth degree on the variables, which means x square or x cubic with that with the target variable. So polynomial multiple regression, which means that with multiple variables and the polynomial, it's actually rarely used. So if we use the mass formulation, simple linear regression is x plus b, and the multiple linear regression is with multiple variables. It can have x1, x2, and xa. Polynomial regression is that x squared or x n degree, x n degree, and I'll go all the way down to x1. Okay, so that's the difference between multiple regression and polynomial regression. We'll cover polynomial regression, but actually this is not that quite used unless you detect a clear shape of the x and y. It's a curve. Okay, then you may use a polynomial regression, but in reality, we don't use that often. Okay, so this time we are looking at a real data set with multiple variables, and do the regression on this data set. Okay, the first thing, the data set I'm going to use is from this class from this package Skylearn, and it has a library called dataset. So this dataset is like a create a class for the dataset, and then people can put their dataset into this class, create this class, and with their own data. And in this dataset, it will define like what property, what attribute it should have, and what functions it should have. So, for example, with this class, it clearly defines with this data, a load. If you call this data set and use this, call this attribute, then it will load the x. And if you call this feature names, it will load all the feature names. And description, it will describe the data set. So it's just like a class user. For example, if you have a data set of your own, you collect it from somewhere, right? And then you want to create it into a data set so other people can use it, then you could use this Skylearn data set. Skylearn data set, this class. For example, in my experiment, we used some special like chemical data with XY, and also has an age attribute. So we have to use a class called in-memory dataset. That is special for like graph data. Okay, then we use this class to create the data. So here, let's load this. Okay, load this. So actually, when I used this method, this morning I found that this data set was removed already from this library. So I had to use another data set as suggested. It's called California housing. Okay, so we are using this data set. So this instance, this one, it gives us all the data about this California housing. And with data, with this one, it stored the X, Y separately. If you call data, then it will fetch just the X values. You can see let's see the sheet. I don't know if it would work this way. So looks fine. It's not callable, so it doesn't let me use this one actually. Then we can put it in a data frame and then do it later. So as you can see, this is a 2D array. And next we can fetch the Y values. Y values is calling this attribute target. Okay, this target attribute is stored all the Y values. Okay. And we can also get the feature names and then print out the description. So you see, it has 1, 2, 3, 4, 5, 6, 7, 8 X variables, 8 features, and has a number of instances over 20,000, which is good. And the X value and number of rooms, average number of rooms per household. And each instance actually doesn't represent one house, it represents one I believe it represents one like block, one area. Says somewhere. See, the target variable is the median house value, the median house value for that district here. See, one row represents per census block group. So a block group is like a unit of several houses, and then get the median value of the target and the median value of the other variables. Okay. All right. So the next thing we like to do is first to create a data frame with data frame for this data, put the X values and then the Y value in this data frame. But right now, it's a data set. The type of these are the data set. So usually what you do next is to create a data frame. Okay. and we give the X value and then give the column names. Give the feature names to the column names. So we call this having. Did I spell it wrong? Did I spell it wrong? Or columns? Okay, now let's print out this shape. So it should have how many rows? I would expect this to have over 20,000 rows, and then how many columns? 8 columns, right? 8 columns here. It listed out 8 columns. So the shape of this X data frame should be oh, yeah, so that's correct. And the next thing we want to do is to add the Y value into this data frame. So we add a new, I could add a new feature called price, and then give the Y value to this column. Y value is the housing. So now this should have 9 columns and over 20,000, over 20,000 rows. Let's print it out again to verify. It's good to verify the data after every step. That's correct so far. What we next need to do is to check the like data type of the data frame. Check whether there is any non-numerical value. So for all those models that we are going to use, they only take numerical values. If there's any non-numerical value, for example, if there's a category, students, different types of students, then you need to transform it into using numbers like 0, 1, 2, 3 to represent different groups. Okay, so that's the first thing you need to do. Check whether there's a numerical, whether there's non-numerical value or not. So here, let's look at this. Okay, so this looks good. They are all float. Okay, there's no string data, like different. But oftentimes, if you download a database from Kaggle or from some website, it has strings, categories, and then numerical data. So you need to change those into using replace, right? To change those into 1, 2, 3 to numeric. Okay. All right. I'll go to next one. Check if there's any missing values. So these are actually clean the data set, see it doesn't have any non-null. Each column, it doesn't have any non-nulls. So if the column has too many, if a column has a null, so what should you do? Or too many nulls, what should you do? You could, yeah, either get rid of those rows, replace it with 0. If it has too many nulls, you just drop that column. You don't use it. Right? So yeah, that's a quick review of what we learned about data cleaning. So that's why like each lesson it's connected with a previous. It's built on previous lesson. So we did check the nulls from this info. Okay. So this is actually a very quick way to check nulls. Okay. Next thing what we want to do is a feature selection. This step is very important in machine learning. If you're not using neural networks, with neural networks, you don't have to handcraft the features. However, if you're just using linear regression or those classification models, you have to do the feature selection very carefully. Theoretically, even if you leave those features non-relevant features to the model, it can still create the model. The way will happen. So, for example, you have a model A x1 plus B x2 plus C x3. But if the x3 is non-relevant to the Y, what the model will do? The model will give it a 0, right? The model should give it a 0. But why we still need the feature selection? Because with more features, with more features, it takes a longer time to compute to the model, to build the model, to compute, and it will add noise to it. So the feature may just have like slight correlation with the correlation with the Y value. However, it will be added into that model, and then it will actually add noise, and resulting the model not that accurate. Right. So that's why we need to do this step of feature selection. Okay. So what we actually need to call is just to call this function. Call this function from pandas data frame correlation, and then it will generate a matrix with all the correlation of all the variables. So it's just using this data frame. See, you see here it generates a matrix of the correlation coefficient between all the variables. How do we interpret these variables?
Closer to one, the closer they are to predicting one another.
Yeah, the close to 1, then the strength of their relationship is stronger. For example, self to self, okay, their correlation is 1, x equals x, and for this one, it's close. For this one to, so we are comparing their relationship with the price, right? With the Y value, and want to find those variables affecting the Y value, right? So what we are going to look at is this, actually this last column. You can see which variables are have a high correlation coefficient with the target variable. Right, so actually it only has the price. I don't know. Only this one. This is the first one has a correlation coefficient close to 0.7. Still not too strong, right? Usually I only select those over 70%, 0.7 or 0.8. 0.8, that definitely means a strong correlation. 0.7, okay. Since this data set, I cannot use any other variable, so I will use this one. But all these just have a non-linear relationship with the targets. This is now close to -1 also. So -1, close to -1 or close to 1, they both mean the strong correlation with the y value. So this is positive. Yeah, this one, of course, this will not give you -1, but will give you a negative 0.5 probably. This one same. This is I think this is strong, probably give you positive 0.7. So a value of 0, that means that there's no relationship at all. Be careful when you interpret the correlation coefficient. Don't get it confused, mix up with the coefficient value ax plus b, a coefficient value, right? That you call y equals ax plus b. A is a coefficient, right? B is the intercept, right? So let me draw something here. So these are the dots, okay? These are the dots. And here, they are all close. Just do another plot. So I have a line, a regression line here, correlation line. And the other one, what will be the correlation coefficient of this one and this one? 0.9, yeah. Suppose this is on here. On the line, yeah. It will be 1, positive 1. How about this one? They're all on the line, okay? All these dots are on the line.
Well,
1 as well, yes. So the correlation coefficient only measures whether the dots have a strong linear relationship or not, whether they all align on the line or not. But the coefficient, this is different. This is the 1, right? Ax. it will be y equals x. However, this will be y equals 0.3x. So that's a coefficient we get, right? Ax. That's the a value we get. That's called a coefficient. However, for correlation coefficient, that measures the strength of their relationship. This is the ideal. These dots are ideal on the line, so the correlation coefficient, both of them are 1. Okay. And yeah, another, if it's closer to 0, then the plot will probably be scattered all around. There will be 0. Okay, so be careful with the difference between correlation coefficient and the coefficient. Okay, and the next one. So from this result, I will just get I will use only this first. Only use this first x value, right? That's a median income.
I think there's another good correlation between average bedrooms and average rooms.
Well, which one?
Between average bedroom and average rooms.
Average room and this one.
Mm-hmm.
Average room and average bedroom. Yes, these are highly correlated, but we are finding the x for the y value. So what we are selecting is the those with correlation, high correlation with the y value. Instead, supposing this is not a good example to demonstrate, okay? Supposing this average room and the average bathroom, they both have correlation, high correlation. For example, if this value is 0.8, this value is also 0.7, 0.8. I'm going to use both values, both variables, right? However, the next thing you need to check is whether these x variables have a high correlation with each other. If the x value, if there's any x1, x2 has a high correlation with each other, you just pick up 1. Pick up 1. Why? Because if the x1 and the x2 have a high correlation with the other, okay, then why? So it has a correlation, high correlation with both x1 and x2. So if x2 and x1 have a high correlation with each other, then this x2 can be explained as cx1, right? Because they have a high correlation with each other. So this will ultimately can be combined into one variable. You just need to use this x1 or x2 instead. Does that make sense here? Okay. Yeah. So other than if you leave it there, it will still give you the good result. But however, you can reduce the dimension whenever possible. So here, of course, both are not that correlated with the y variable. We are not going to use it, either of them. But if there's any variables, X variables have correlation with each other, then you should just pick one of them. So that is checking the correlation of the features and the correlation between the feature and the Y. Okay. The next thing is that you can just use a scatter plot to verify the correlation between the Y variable and then the X variable we selected. We can do that. Let's do this quickly. Actually, this step is not necessary, but you could do a scatter plot to verify the correlation. Right? This is not necessary, as because we already calculated the numbers, but you could add this one. Yes, you see. So that's kind of 0.68. Yeah, it's not very strong, but it's kind of a linear relationship. Anyway, this is the data set we are using, so this is the only variable looks of we could use for predicting the price. Although this is not directly related to the house price, you see income. Income is actually not related to the house at all. But this is what the data set provide. You can use this. If you are doing a real project, I'll probably just discuss this idea to predict to use this data set, because we all know income, it's not directly related to the house price. It's not related to the house at all. But we are just demonstrating building the model, okay? So I'll update the slides because it used the slides used a Boston housing price, which was better. Next thing we needed to do is to split the data set into training and testing. Because if we use all the training data, for example, the height, okay, the model may fit all the training data, however, may not be able to predict the future data. So what we usually do is to split it into training data set and testing data set. This is the ratio we often use, 70% and 30%. And the method we are using is called train test split. Okay. So what this one does is you just what this method it takes is you tell it the things you need to, you tell it the X and the Y you need to split. and you tell it the test size, the size of the testing size. Testing size maybe 0.3, and random state. So the random state it defines it fixes how the data is split. If the random state is 5, correct, then I may take a 1, 3. It may follow a pattern 1, 3, 10. Take out all those data randomly, right? So if the random state you change it to 6 or 7, then it takes out the different data. So if the random state is 5, every time you run this line, it takes the same data. So this helps to the reproducibility of the experiment. So if you don't fix this one, okay, this time when I do the experiment, I get the result, get the data, hey, 1, 2, 1, 3, 10. And you may get John when he does the experiment, it may take out the different data, 2, 4, maybe 8. And then hey, our result will not be the same, will not be exactly the same, right? So that's why usually you fix a random state. Okay, give it a number. It could be fine. It could be any number you want. But if you give this, then when I run the data, when I run the experiment, it gives you the exact same data as when Dion runs the experiment. It's like the seed. When you generate the random number, use those random function, you often want to fix the seed. So like a random number, right? When you call this random function, usually you add a seed at the top. At the top. So every time you run this random function, it gives you the same random numbers. This actually the training testing data set, it split this function. What it does is actually it just generates some random numbers and then use these random numbers to get the rows, to get this. So that's a quick explanation of the random state, okay? It's not very hard to write a training testing split by yourself. Actually, we have learned the I location, index location, where the generator 0.3 times the length of the data set, generate a list of the random numbers and then take out the cases. So here X. So we want to give it the X and then give it the Y. Also here the Y is just the housing EF price. And the X is we only have one variable now, unfortunately. Okay. Now I need to give this result. So this returns the X, Y value that are splitted. You can give it a new variable called X train. It returns the because you split it two variable, it will return the four argument, four arguments. So you can name it X train, X path, and then Y train, Y test. Okay. If we verify you can verify the shape. There's some problem. So the ratio, the rough ratio for this should be 7:3. Is that correct? Doesn't look 7:3, right? Oh, it's roughly 7:3. 7:3 is like a 2:1. So it's roughly 7:3. That's correct. You can just do the estimate. 0.7 to 0.3 is roughly 2:1. So this one is a kind of a 2:1, a little bit over 2:1. That's correct. Correct. Okay. Now we can use the model fit and the model predict we used at last time to do this. Okay. So what we need to do is to use the training data to build the model, and then use the testing data to verify the model. Okay. And we already learned this, right? Last time. But what should I feed to this function now? Fit. What should I feed it now?
Train and Y train.
That's right. There's a problem with the shape problem. See, it's expecting, and this X this X train is like a one dimension now. So we need a reshape. Still gives me the error. Then I have the attribute reshape. See what I used here. I think this doesn't need the because usually you have a multiple variable in the X train, so it has 2D, and it doesn't need that, and it doesn't need to transform the shape. So here we probably need to transform the X train. Let's try to see what's the find the CRV. And what does the error tell us to use? So it does tell us to reshape. Anyway, we could change this to numpy array first and then do this. Now let's look at the shape again. Yeah, so now it has one here, so at least two-dimensional. Let's try this again. See here, so it worked fine after we changed the X train into a 2D shape. This works fine now. All right. Let's continue. So we built the model. Now we need to test the model, right? All we need to do is to model predict. For model predict, we need to use we use the testing set to predict the model, right? Model predictor, what we need to use here. X text. And then this is the Y predicted. Same again, you need to transform this X test to shape, to the 2D shape. All right, let's use this on X test. But usually if it has multiple variables, you don't have to go through this step. Okay. Here, will predict Y predicted, and then you can use either R squared, or what we also learned the MAE or MSE, mean squared error, mean absolute error, or R squared to see whether this model is a good fit to the data or not. How accurate the model is. So here we use R squared, and R squared, we said you just need to model dot score, and then you just need to give it the X data and the Y data, and it will give you the score. Okay, see, okay. It's not very high, not a good model. So, okay, so obviously this is not a good model we built, but sometimes when the data is not that good, okay, whatever model you build, you cannot do a very good job on the model. So, and this one we already did it last time. I don't want to go over that. You just get the intercept and the coefficient. Now, that's why it's really important to check the relationship of the variable with the y value. If the correlation of the variable is not that strong with the y value, even if you build the model won't have a high R-square score. Right? It won't give you a good model. This just doesn't have a strong relationship, correlation relationship with the y value. Okay, so here, let's move on to quickly talk about polynomial regression. So here I just made up some data again. For this data, you see if I find it there. Okay, here for this data, you can see the line doesn't fit very well. However, the shape of this dot is clearly it's curved. Here at this point, it's clearly curved over this way, and then you can use the polynomial model. Right? So how we do that? It's actually exactly the same as the linear regression, 1 degree linear regression. However, you just added one step. So polynomial regression, usually the relationship between x, y is for 2 degree, it's in this shape, or it's in this shape, right? Flip this shape. For degree 3, if you add x cubed, then this will have another hump here. It will be 2 hump, a curve, and the degree 4 will have more freedom. Okay, so that's the shape of the polynomial functions. So you have to clearly observe the data and know what function will fit it. The rest for polynomial regression, actually, the scalar, it doesn't have a model called polynomial function. What it does, what we do is to transform the x variable. For example, right now we only have one x, right? So what we do is to add a step here to transform this x into several variables. It could be you add x squared or you add x cubed. Those are x to the power 3. Okay, so that's what we do to do that. That's how we do the polynomial regression. So this is a step here. This is a function here. This function here, I cited this function, and then you tell it how many degree you want. If it's a degree 2, it will give you x squared, and 1. So x poly, okay, just x poly. Of course, let's define xy first. and X poly equals this instance. So this is a class, and I created an instance for this class, and then you use this instance to transform the X. And if you see the X poly, the new X poly, so that's X poly instead of X is 1.52, this middle column, right? So after applying this function fit transform, it gives us 1x and x squared. So now I have x and x squared. Then I can do the linear regression to write ax plus bx squared, right? Are we all good here? John, yeah, any questions so far?
No, very
That you can get rid of this one. You actually doesn't need this one. But you need the x and the x squared. We want to build the model ax plus b ax squared plus bx, right? So this will be like x2. This will be x1, and this x squared will be x2. And now you can use a linear regression again. You need to do is to use that linear regression. I'll call this the model 2, another model, right? And you can use model 2 to fit the X poly, the new X. The new X we got is we name it X poly, right? And it has a kind of a 2 variable. One is X, one is X squared. And then Y is still Y. And then let's build the model. Okay. So and then you could use this to predict the data to dot. Be careful here. Here, should we use X or X poly? Yes, you need to use X poly. Be careful, if you transform the X, then when you predict, you also need to apply this same transform to the one you need to predict. So here the model we built here is the model we built here is Y. Y equals AX. AX squared plus BX. bx. So if you don't use that x poly, you actually give it an x, it should report an error because the model has the two. This is the x1 and this is the x2. Actually, it should report an error. So this is the x1, this is the x2, and now if you give it x, you actually give it only one variable. I would expect it report some error. See, it did give us an error. See, x has one feature, but this model is expecting 3 features, 1 x and x squared, right? So this is just a case there. And in the future, we'll do a lot of transformation on the x and same. If you transform the x and then you didn't transform the x test, then it will have a problem. So okay, so then this prediction function will work appropriately. I don't want to repeat these the way we did it. And so with these coefficient, and after you get the intercept and the coefficient, you can build the equation. The equation should be this is the x square and this is x kind of negative 0.2 x square plus 2.2 x, right? We are correct here, and plus this intercept. I mean the equation for this model. Yeah, this is the 1, this is the x, this is the x squared. So if the coefficient is this, the equation should be a 0. This one times the x squared and this one times the x plus this one times the x and the plus the intercept here equals a y, right? And yeah, if we change it to a higher degree of freedom, and then the line will just have more curves, more humps. Okay, the next thing we want to talk about is the bias and the various variance trade-off. Okay, if, for example, this line, it doesn't fit the training data like the one we built here. The R-squared score is very low, then the bias is very high. Okay, probably you could do a multiple degree model to fit this data, fit it very well. Then what will happen? Variance. This is variance. Yeah. So you find a model to perfectly fit this data, and then what will happen is if another data is here from the data set, then it cannot predict this very well. So you call it high variance. High variance. Okay. So for this one, okay, this one probably should be able to predict these pretty good. But for this model, although it fits the training data very, very well, it cannot predict the testing data very good. Okay. So this model is called a high variance. It overfits the data of the training, overfits the training data. Using these 3 pictures shows that this overfitting. So this model, the red line is the model we built. It fits all the data, but it doesn't have good generalization ability. If it comes with another data over here, probably just over here, the point I'm pointing to, then it probably cannot predict very well. And this one, it has a high bias. It didn't fit the training data very well. A good model should fit the training data, however, have the keep have a low variance as well. So what we usually use is to use a total error, which means that because we want to find the model have both a low bias and a low variance. So what we use is the total error. That is the bias plus variance, or bias square plus variance, and to find the minimum number of the total error. Okay. So let's conclude our lesson today, and in the assignment you will have a similar task to build the linear regression, simple linear regression, and multiple regression with different variables.